Hello, good evening, and welcome to our discussion on the principles of physics. So we begin our learning of the principles of physics by first recognizing that physics is the center of all the sciences. In fact, we have many hybrid sciences that are mixed with physics, like biophysics. This is biology and physics. And physics is found in all aspects of our daily life, but it started as, before being known as physics, it was part of natural philosophy. So this, what's used to be known as natural philosophy, included all aspects of nature by bringing in together physics with other fields of science, such as chemistry and biology. But now physics has been separated, and it mainly focuses on explaining the most fundamental aspects of our universe. And this is this four corners of the square: this motion, energy, matter, and space. Motion, energy, matter, and space. Now we are so concerned with relating the study of physics to the studying of the effects and the causes of motion, energy, matter, and space to our universe. Although physics has this autonomous, distinct um, field of study, but it still can then, even though physics separated from natural philosophy and it became the study of motion, energy, matter, and space, then it was combined, as I mentioned, as a hybrid with other sciences, as we said, the biophysics, the biology, and the physics of biological systems. Now, we must first outline the difference between observation and hypothesis. So, an observation is a pattern or trend that a person notices or sees in nature. So, an observation is something that is based on the senses, something that you heard, something that you have seen, something that you have thought of. But hypothesis is based on logic and reason rather than an observation that could be um, clouded with emotion. So, an observation can lead to a hypothesis, but a hypothesis is a more formal, more logical, educated guess that attempts to explain something about this observation that we sensed. And, this is happening in daily life. I mean, you have an observation that your car is getting too hot. And then your hypothesis is maybe the radiator doesn't have water. I need to add water to the radiator. So the observation led you to the hypothesis. So the observation leads to the hypothesis. We would not have a hypothesis unless we had an observation that triggered our senses to notice something. And based on that, we are able to devise a hypothesis. And then this hypothesis, we must run it through filters filters that ensure that this hypothesis is testable. We cannot test something like the souls of the dead bodies are ghosts, something like that. That is not testable. Even though we may have an observation that dead bodies may seem scary or cold or, frightening, but that could not lead us to an illogical hypothesis like ghost or things like that. So we need to have a hypothesis that is based on an educated, um, testable experiment. And then we have the next level of the hypothesis is a theory. A theory is a hypothesis that underwent extensive experimentation and testing, and we got scientific support. We have data that support that this hypothesis is likely to happen. So what are the models? Models are a very important part of our understanding of physics. Modeling is useful in studying the structure of the atom because models replace the real atom with something simpler that helps us understand, that has similar features and similar expected behavior. For example, the planetary model that the sun is in the center and all the planets are revolving around it. This model that inside the nucleus you have protons and neutrons, and circumventing around them are these electrons. Is this what really happening? Is the sun in the center and all the planets are spinning around it? No. Is the electron, are the electrons spinning around the nucleus, and you have proton that looks the way the model looks? No, that's not true. But it does give us an understanding. It gives us some confidence into having a mental picture. So sometimes you can have a model. For example, if you're driving your car, you're looking in the GPS, it tells you that's the street, turn left, turn right. Is that picture you see on the GPS exactly what the street looks like? No, it's not. But it's a model that helps you develop a mental picture. Then what is the difference between a hypothesis and a theory? A hypothesis is an experimental test and doesn't necessarily need much evidence to prove the case. So the hypothesis must be testable, but it does not have to be proven. It could just exist as a hypothesis. If this happened, then that happened. If you increase the temperature, the enzymes will denature. That's a hypothesis. Hypothesis always begins with if and then. If this happened, then as a result, that will happen. An action and a reaction. That's a hypothesis. But a theory has been proven and needs to be supported by retrials. For example, then if I change from saying if we increase the temperature, the enzyme will denature, that's a form of hypothesis. But if I say increasing the temperature denatures the enzymes and decreases the concentration of the products, we will no longer be having products because the enzymes who catalyze their reaction have been damaged and destroyed and denatured. Well, something like that is no longer a hypothesis now, because now I am not saying if and then. It's not hypothetical. This is now a theory that was based on experiments that have been devised. We have put the enzymes in test tubes and heat up the test tubes. And then when we put the enzymes in the reaction was not catalyzed, indicating that the enzyme was damaged. So that shows you now a theory needs evidence and experiment. So a theory is a scientific explanation that has been repeatedly tested and validated over and over again. What is relativity? Now, this relativity is a very big idea. It was a theory that brought together by Albert Einstein. So Albert Einstein devised this theory of relativity based on gravity. Relativity is all about gravity. In fact, there's two types of relativity. There is general relativity and there is special relativity. Special relativity is studying the concepts of physics in the absence of gravity, while general relativity is studying physics and the implications and the effects of gravity on the physics laws. So we learned through relativity that gravity is the result of the bending of time and space. So now they realize that time is not this just invisible thing that's happening, that they are now believing that time is an actual dimension. And if you travel with a speed that is close to the speed of light, then you can actually slow down the time. So everywhere we know what a second is, we cannot stop the time goes on. But they saying now, if you travel in space with very, very, very high speed that is approximately closer to the speed of light, then the time will move slower for you. The time will move slower for you, so you will not age as much. So spending 5 years in space is not gonna is your age you're not gonna age as much as spending 5 years on Earth. So gravity or the speed of the observer can affect what they observe as the measured time interval and the measured distances as occurs with the length contraction or the time dilation. So the time is going to increase if you're moving slowly. And we notice this. I mean, if you're moving fast, you feel like the time is really moving slowly. But if you are moving slowly, you feel like the time is going really fast. So relativity is all centered on gravity primarily. This is the closest galaxy to us, known as the Andromeda Galaxy. It's in our Milky Way um, galaxy. It's the closest to us. And, we have to have an idea of studying what is the universe that is surrounding us. And that is going to depend on our understanding that scientific explanations may be supported by all the available evidence at a particular point in time. But science never precludes the possibility that some future observation could contradict the explanation, meaning that no physics law is can never be rejected or disproven. That's not true. That's why we need to repeat the experiments and subject our old ideas and concepts into further, more rigorous testing to see if the concepts will hold true. But what we need to understand is that the physics laws, they are true in space, they are true on Earth, they are true in the ocean, they are true at the level of the atom, the subatomic particles, they are true at the level of microcosm. Physics will always be physics. So this shows us here the GPS and how, the engineers are going to put together electric circuits to help us establish a relationship between the distance that we're to trying to cross and the time it will take us to get there, depending on the speed of the car that we're driving. So your GPS is constantly adjusting based on the speed that you're taking and the traffic ahead of you. How long is it going to take to that destination that you're trying to get to? So we must understand the difference between classical physics and modern physics. Classical physics has three laws. The first law, matter must be moving at speeds less than about 1% of the speed of light. So if we are dealing with classical physics, we are studying particles that are moving fast. By the way, 1% of the speed of light is pretty fast, but it must not be that fast more than 1% of the speed of light. So classical physics can only apply to going at speeds of 1% or less of the speed of light. Not only that, another requirement, we must be studying macroscopic particles or microscopic particles that could be seen with the naked eye. How far the missile is traveling and the car we're driving. These are things that are at the level of the macrocosm. So microscopic, not subatomic particles, as well as those visible. So we must be, classical physics must include things that could be seen with the naked eye. And lastly, the gravitational field that is affecting our experiment must be a weak gravitational field like the one that is generated by Earth, not something that a big field like the one generated by the sun. So these have to be the three laws. Something that's big, something that's moving slowly, but if it want to move fast, it can move only as fast as 1% of the speed of light, not more than that. And our system must be under the effects of gravity that is only weak gravitational attraction, like the gravity of the Earth, 9.881 gravitational pull. So physics is useful in weather prediction because the physical laws of motion and energy govern the movement of air masses and energy in our atmosphere, which is what generate the weather. So we're studying, remember in physics, we're studying matter, we're studying motion, we're studying space. So it's very important we outline this square that, we have motion, energy, matter, and space, and that we're gonna understand these dimensions only through physics. And this here is found in this structure is found in England. People used to they say this was thousands of years ago. People use it for, religious purposes or, to look at the stars and the day in which the winter the time will change where you'll have the shortest day in the winter. That's gonna be about, the sunrise is gonna rise, the sun is gonna rise at 7 a.m. and it's gonna set at 4:30. That's the shortest day in winter. I mean, you're gonna have the longest night in winter. So people used to years ago, experiment with physics in this very important structure. So um so So the physics is useful in weather prediction because the physical laws of motion and energy govern the movement of air masses and energy in our atmosphere, which is what generates the weather. And we must understand what is a physical law. A physical law is one that explains a specific physics phenomena, such as how the force of gravity is based on the mass of the object and that object's distance from other objects. So to be universal, this law should apply everywhere in the universe. We mentioned that to be able for the physics law to be universal, it must be correct when applied at the subatomic particle or even at the microscopic or the macroscopic level. So the magnetic resonance imaging here uses electromagnetic waves to yield an image of the brain, and the doctors can use to find disease regions like tumors and stuff like that. Also, we see physics is important in the physical therapy. So the physical therapist must understand how muscles generate the forces that allow the body to move and bend. And the physics allows us to understand how the muscles generate the force. And that is through the action potentials. And you have the innervation of the muscle, the action potential innervate the muscle. And when then the muscle is under the innervation, of the nerve, the muscle is going to contract. And when the muscle contracts, it's going to be extensible and it's going to shorten the sarcomeres are going to get shorter, and the shortening of the sarcomeres is going to pull the bone, and that's going to make the flexion of the joint or the extension of the joint. Now, now back to Einstein's theory of relativity. That's a theory that describes space and time as an interweaved mesh. So a large object such as a planet, like the planet is in the middle and it's like you drop a big bowling ball in the bed. So you see it's gonna spin and center itself in the bed. Then if you drop some marbles around it, all the marbles are going to start rolling into the center where that big ball is. So that's what's happening with the Earth. You see all these little in space. So you think space is empty, but space is like a mattress. And the bigger the object is going to attract around it, all of these particles. So the large objects such as the planet, they distort space, causing the objects to fall in toward the planet due to the action of the gravity. And large objects also distort the time, causing time to proceed at a slower rate near the surface of the Earth compared with the area outside. So you see the Earth is spinning and then the sun spinning, and you have Jupiter. So the bigger the object, the more likely the stars and those satellites are going to be spinning and falling in its hole, in its medium around it. So the theory of relativity is considered part of the modern physics because it was um, developed alongside other far-reaching scientific advances in the 19th century. And these advances radically changed ideas in physics from those accepted in the classical period that was by Newton and Galileo, dealing with really big objects that are seen with the naked eye and under weak gravitational attraction like the Earth. Okay, so this shows us how physics help us when we use a scanning, tunneling microscope. Scientists can see the individual atoms that compose the sheet of the gold. So here we use the technology of physics and the optics to be able to visualize these little microscopic segments. This is a particle collider that helps the object move at speed as fast as the speed of light. So when they want to do an experiment to make an object move at the speed of light, they put it inside this huge collider. And it allows the subatomic particles to be accelerated to near the speed of light. So something inside this collider could go so fast, like the speed of light, and then they can do the experiments there, and that's how they learn about it. Why can't you put metal in the microwave? So microwaves are high energy radiation that increase the movement of electrons in the metal. You know, metals are atoms. They have electrons spinning around them. So these moving electrons can create an electric current, causing the sparkling that leads to fire. So the waves that are going to be the wave energy is going to be absorbed by the electrons, causing the electrons to jump up to higher levels in the electron shells. And these electrons can create an electric current, and that current can lead to the fire. So physics, chemistry, and biology help describe the properties of the cell walls. That's why we said there's a biophysics. We study the physics of the structural integrity of the plasma membranes, for example. So this is a spacecraft with large revolutionary solar panels that carried or this satellite has a lot of technology that enables us to study what's happening in space. And the lander then detached and landed on the comet. So this enabled us from Earth to see the comet and to get fragments like a biopsy and bring it to Earth and study it. Okay, so this shows you the gravity of Saturn so that shows you in the center, the bigger the planet, the more it's going to attract around it. It's going to attract little particles around it. So that's what we talk about when we say the model. So the electron cloud model of the atom predicts the geometry and the shape of the areas where different electrons may be found in an atom. So it cannot indicate exactly where an electron will be at one time. So that shows you that electrons can be found. You know, this is like if you freeze or take a snapshot of the atom, the electrons may look like that, but actually the electrons are spinning and they're moving. They don't stop. But this is just a model to help us visualize their geometry. Okay, so distances given in unknown units are maddeningly useless. We talked about this in class when we said that we need to establish units that are universal. So wherever you go in the world, everybody knows what a meter. You can ask somebody in Japan, somebody in South Africa, somebody in Mexico, somebody in France, tell them where is the next gas station, and they will say about 2 kilometers. Everybody knows what that is. But if they say it's about 200 cables, you have no idea what a cable is or how long is that. You don't have any emotional or you don't have any understanding or a mental picture of how long it may take you to get there. So that's why units are there to help us have have a common understanding of units. Okay. So the meter is defined to be the distance that light travels in this amount of a second. So not even a whole second, in about 1/299,792,458 fraction of a second. So that's how they are able to make a firm definition of what a meter is. You cannot say the meter looks like that, and then you do an arm span. I mean, your arm, my arm, his arm, her arm, they're not the same. But when you say the light is the same, and the second is the same, so now that's a very standard way of now we have the distance, and now we have the time, and and we already know the speed of light. So now we know that if we have this, we know that distance we know that speed equals distance divided by time. I have the distance 1 meter, so it's going to be the time times the speed of light will give you 1 meter is this. So that just shows you how we're able to fixate a definition for what is basically 1 meter. So an atomic clock, such as this one, uses vibrations of cesium atoms to keep time to a precision of 1 microsecond per year. So this is the fundamental unit of time is the second, that's the SI unit. It is based on such clocks. So this image is looking down from the top of an atomic clock. So that shows us, the really small phytoplankton float among the crystals of the ice in the Antarctic Sea. So we're able to see this that is as small as few micrometers to as much as 2 milliliters in length with the technology of the microscopes. So there are theories about how galaxies collided about 2.4 billion light years away from the Earth, and that's a tremendous range of observable phenomena that we can see right where we are from Earth. But the distance from Earth to the moon may seem immense, but it is just a tiny fraction of the distance from Earth to our closest neighbor star. So that shows you that space is really, really vast. Now, this shows you the concept of, this is a measuring weight. So for example, if you want to buy sugar in underdeveloped countries, they don't have the electronic scale. So what happens is if you want 1 kilogram of sugar, they would put 1 kilogram on one side, then bring a bag of sugar here and start to fill it with sugar until both are even. And that will tell you, because we already know that this side is 1 kilogram, the more sugar you add here, and when they're both are even, that means that the sugar in the bag is about 1 kilogram. But there's a lot of uncertainty that is involved in that. So the uncertainty is a quantitative measure of how much your measured values deviate from a standard or expected value. So a double pan, this is a double pan balance, and it's used to compare different masses. So usually an object with unknown mass is placed in one pan, and objects of unknown mass are placed in the other pan. So when the bar that connects the two pans is horizontal, then the mass in both pans are equal. So you need to know that the uncertainty is when we study how far off is our measured value from the expected or the actual value. This is a mechanical balance may only read the mass of an object to the nearest tenth of a gram. There are some digital scales that can measure the mass of an object up to the nearest 1,000th of a gram. So that is definitely more accurate and more precise as in the measuring devices. And we discussed in class that the concept of accuracy versus precision. Accuracy and precision both describe measurements. So we have 4 measurements, 1, 2, 3, 4. How close are they to each other? that makes for precision. How close they are to the bull's eye, that makes for accuracy. So accuracy is how close are we to the target, and precision is how close are the values to each other. So the black dots represent each attempt to pinpoint the location of a restaurant, and the dots are spread out quite far apart from one another, indicating low precision. But they each rather close to the actual location of the restaurant. So here you see that they are far from each other. So that's low precision, but they are close to the center. So that makes high accuracy. But if you look here, they are far from the center. So they are not accurate, but they're close to one another. So that is high precision. The dots are concentrated close to one another, indicating high precision, but they are rather far away from the actual location of the restaurant. So here you see both. They are close to each other and they are on bullseye, indicating that they are rather away, indicating high precision. So here they are close to the location of the restaurant. So the location of the restaurant is in the middle. So that is high precision and high accuracy. So this shows us 3 metric rulers. The first ruler is in decimeters and can measure 0.3 decimeters. The second ruler is in centimeters and can measure up to 3.6 centimeters. The last ruler is in millimeters, can measure up to 36.5 millimeters. Now we can refer to units like a bank stack contains about $100 $100 bills and is worth 10,000. How many bank stacks make up $1 trillion? Okay, so this graph here shows us independent versus dependent variable. So the independent variable is the time. It does not change. It goes on and on. It is the dependent variable that is going to change based on a relationship with the time. So your distance from the station, you could go far or come near. That all can depend on the time. So in the morning, you're close to your house. In the afternoon, you're really far away from your house because you left to the hospital, you will left to your work. At night, you're back closer to your house. So the distance from your house, that is your dependent variable, but the time is independent. So this shows the graph of the train distance from the station versus the time. And the independent variable does not change as a result of the changes in the dependent. The dependent variable, on the other hand, changes as a result of the change in the independent variable. So the train in the beginning was really in the station. It's not far from the station. 10 minutes later, the train is 20 kilometers away from the station. 20 minutes later, the train is 40 kilometers away. 30 minutes later, the train is 60 kilometers away from the station. 70 minutes later, 70 minutes ago, the train was in the station. 70 minutes later, the train is about 140 kilometers away from the station. So that shows you the distance is dependent on the time. The time is not dependent on the distance. So that is the trend line that shows us how close the points are to this line, indicating accuracy. So the closer you are with the closer these data points are to the line, the higher the correlation, the closer the correlation coefficient to 1, and the more appropriate and the more accurate and precise our numbers are, data. So example A shows us a linear graph. You see, the red line is linear. That's a whole line. B graph shows us a quadratic. That is a quadratic curve, while C is a form of an inverse curve, and E is a form of and D is a form of an exponential relationship. This is the Richter scale used to assess the earthquakes, and it shows us that the relationship between frequency and wavelength. This here shows us the relationship between frequency and wavelength of the electromagnetic radiation can be plotted as a straight line. But the Richter scale, because it uses the logarithm, that is the log base 10 scale, it must actually be in the form of exponential. This is a form of an exponential curve. Okay, so when we graph the line, we graph rise over run, rise over run. So here, if we want to know the slope of this line, we rise by 20 points and we run 10. So it's 20 divided by 10, which is about, the slope here is about +2. So +2, that means you go up 2 and you go to the right 1 unit. So it's 2 divided by 1. So both are in a positive direction. So this is the positive y-axis. This is the positive x-axis. Below is the negative y-axis. And to the left is the negative x-axis. So we go up 20, right 10. Up 20, right 10. Up 20, right 10. Which is the same thing as we go up 2 orders of magnitude and 1 order of magnitude to the right. We rise 2 orders of magnitude, we run 1 order of magnitude. Thank you.